Professor said, I'm Nandakishor. I'm currently doctoral student at Institute of Chair of Materials for Additive Manufacturing at ONIBV. So for this work, my team includes Frank Ajay Chairman from RWTH, Aachen, and his Professor Iris Afez, and my master thesis supervisor, Dr. Chris Hull from KTH. So the work is numerical modeling of metal melt droplets, cooling and solidification during gas atomization. So as we all know what the gas atomization process is, here you can see a schematic in which in the process the metal melt is actually hit by a high pressure gas stream, which breaks the metal melt stream into droplets and further cools it down to powder particles. So the gas atomization produces very fine spherical powders in micron scale with diameters in the micron size. So here is an image of a powder particle produced by gas atomization. It's taken from Aachen. So the process includes very rapid cooling and solidification in the range of 10 to the power 5 kelvins per second, and produces very fine microstructure due to high cooling rate, and involves two important processes, nucleation and solidification. And the process is really hard to monitor as it occurs at a high temperature inside a closed chamber. As you can see in the graph, it goes to 1200, 1300 degrees Celsius, and yeah, it happens really quick. So the particle diameter usually will be over a broad range from 20 microns to 200 microns. So the atomizing controls have a significant control over the quality or the properties of the final powder particles produced. So why is numerical modeling important for gas atomization? So understanding droplet thermal history is really important to predict what is actually going to come out of the gas atomizer. So the morphology of the powder particles and the mechanical properties of the end product created from that actually depend on how we make the powder. So understanding the cooling rate and other process parameters and foreseeing what are the final end product is an important step in understanding the process. So, and also the prediction of the nucleation behavior is also critical, because a change in composition can lead to a completely different type of powder particle being produced. And also with the current technological developments, we are unable to monitor the gas atomization experimentally, or we can't access the nucleation or find the nucleation temperature or nucleation time during the process experimentally. So we have to reach out to other techniques, which one of them is CFD, where we can actually do the fluid stuff and can only predict gas vectors and recirculation, but we are unable to reach nucleation aspects or events. And then there is the phase field modeling, but requires a huge amount of computational power and can only simulate one single droplet, maybe even not the whole of it at a time. So that's why we are trying to look into numerical models. And there have been numerical models already been developed, but most of them are able to handle only basic alloys or binary alloy systems. So aims of my project. So the goal is to develop an improvised physics-based model for predicting phase fractions formed in a population of gas atomized powder particles, and predicting the nucleation temperature using a stochastic technique. Prediction of spread of nucleation temperature for different droplet sizes, which I will talk about it later. And effect of an alloy composition on the phase being nucleated, effect of atomizing gas and droplet size on the nucleation temperature and the cooling rate. So yeah, let's see what had been happening in the field. So in 1989, Lavernia and Barham had their study on droplet solidification, and they observed that a changing processing condition can lead to different dendrite arm spacing for the particles of same size. So droplets of same size create a different morphology when they were processed under different conditions. And also the solidification features are influenced by process parameters, including cooling rate. Later, Lee and Ann in 1994 developed a model for solidification progress and heat transfer analysis. So the model was expected to predict gas and droplet velocities in the process and fractional solidification. They introduced the concept of spherical growth of solidification front in the droplet, and they coupled Newtonian heat transfer formulation with classical heterogeneous nucleation theory to develop this model. Later in 2000s, Bergman et al. Developed or improvised the Lee and Ann model. They included nucleation rate analysis in the model. They used the classical nucleation theory. They tried to compute the number of nuclei formed in a given time strip. And from there, they computed the nucleation temperature when the number of nuclei formed in a time strip was reaching 1, a value of 1. So the issue with this model is that if you do this model for 1,000 repetition, you will be getting the same value for every droplet size you are calculating. So that's actually not what is actually happening in a gas atomizer. So for the same droplet size, you are getting different temperatures. So we need some method to replicate what is actually happening in the real life. So our model, we are actually developing this model based on the work from Bergman et al. And Lee and Ann. So this is our cooling in liquid state, where the differential equation for the temperature change is taken, where the convection and radiation heat transfer is accounted. As you can see, the two terms in the equation. And then we have the nucleation kinetics, where the classical nucleation equation is used to compute the nucleation rate. And from the nucleation rate, we are computing the number of nuclei, which is the N, which is essentially a value multiplied, the nucleation rate multiplied with the droplet volume and the time strip. So from this, we are computing the nucleation temperature. Instead of computing the nucleation temperature from the number of nuclei when it is equal to 1, we are doing stochastic techniques. And from that, we are computing the nucleation temperature for a population of droplets rather than a single droplet. So what we are changing here is that using the stochastic technique, where the number of nuclei formed in a time step is essentially the probability of nucleation, the event of nucleation happening in that process. So we are comparing it to a random number generated by the computer. So when the probability of nucleation is more than the random number generated, we are actually accepting that, yeah, the nucleation is happening, the nucleation happened. This actually predicts a range of nucleation temperature for droplets of similar size. So when we are comparing the random number, the nucleation temperature is identified at different time steps for different iterations, even if the droplet size is same. And this is actually giving us a result which is more closer to the real scenario. And also we are using live thermodynamic data for the computation. We are using the TQ interface of Thermocalc software, which is actually a software development kit, where the program, our model, access Thermocalc software behind the computer and takes the values, live thermodynamic value for each time step, and updates it for the time step and computes the results. So this helps to this leads to very less requirement of very basic data from the user, and the program is made flexible so that any alloy composition can be used or updated, and we can find the results for that. So the assumptions taken here are the droplets are rigid spheres. Droplets exist at the start of the simulation. The droplet is so small and metallic so that it's having a homogeneous temperature inside it, and a constant gas temperature is expected. And single nucleation even leads to the complete solidification of the droplet. And the nucleation is expected to occur at the surface of the droplet, and curvature of droplet curvature of the solid liquid interface is equal to the curvature of the droplet surface, and wetting angle is independent of the droplet size, and initial temperature is not affected by the melt breakup. So the input data a user have to give to the model is the composition that he uses. These are the compositions that we used, when we can see the results later. And then the database which must be used for the composition, which is from the Thermocalc. So here we use TCFE. Then process start and end temperature, and process conditions like gas temperature, emissivity, initial density, gas velocity, etc. Then the phases needs to be tested. So the user have the flexibility to test any number of phases for the nucleation, and the program says, yeah, this is the phase first nucleated. And then the surface energy, wetting angle between the liquid and first solid phase, and then the gas thermophysical parameters like gas viscosity, density, specific heat capacity, and thermal conductivity. So these are the limited amount of data that the user have to give to the model. So moving to the results. So here you can see the liquid state cooling curve according to the droplet sizes. The small droplets nucleates faster compared to the bigger droplets, which is actually what the thermodynamics says. So yeah, the cooling rate is really high for smaller droplets and lesser for big droplets. And here is the effect of atomizing gas on the properties. Here you can see individual numerical experiments for both gases, argon and nitrogen, for the composition given here. So yeah, you can see the spread of nucleation. Instead of a single point or a constant value given as a result, we are getting a spectrum or a range of solidification temperature for same droplet size. So this must be what exactly is happening inside a gas atomization chamber. So here it is 100 iteration of the nucleation calculation routine for each gas. So the next result, this is the effect of droplet size on nucleation temperature. So we have 6 different droplet sizes, and 100 iterations are done. So for each droplet size, 100 droplets are computed, and the nucleation temperature is taken as a result, and they are plotted. So we can see the spread of nucleation temperature, and as we can see, towards the bottom, it's the 20 micron droplet, and towards the top, it's 180 micron droplets. So the average nucleation temperature is directly dependent on the size, if you see this graph, but individual nucleation temperatures vary along these error bars. And here you can see for a droplet size of droplet size of 80 microns, there is a droplet which can actually nucleate at a lesser temperature than a droplet of size of 50 microns. So this is what is actually happening in a real life scenario, and which can be actually modeled with this model. So moving forward, alloy composition and the nucleating phase. So since one of our assumption was that the first nucleation itself reaches the solidification. So here our model actually predicts which will be the first phase nucleated according to the composition. So we tried 3 different compositions, and for the first case, first and second case, FCC nucleates before BCC. But if you look at the second case, you can see the nucleation temperature difference. The difference is higher because the composition changed, and we have increased the amount of carbon and nickel, which are actually the liquid stabilizers. And in the third case, BCC nucleates before FCC. And it's also, the composition is having very less amount of carbon in it. So a change in composition can actually lead to a different first nucleating phase. And this also opened the door to the possibility of overlapping nucleation ranges, where in the real life scenario, we see powder particles or a set of powder particles where the 90 or 90+% of particles are of one phase, and a few of them are having a different phase. So this may be due to a change in composition, which might be happening during the process. And then we compare our results to the previously reported values. We had four tries. So the first one is actually the Bergman criterion, where the nucleation is expected to happen when the number of nuclei crosses the value 1. We tried with the live thermodynamic parameters with the numerical model for the composition given, and minimum droplet size nucleated at 1691 Kelvin, and the 180 micron droplet nucleated at 1695, which is showing a nucleation range of 4 Kelvins. And then we tried our stochastic model, where the nucleation probability is computed against a random number, and it also showed a nucleation range of 4 Kelvins. But with a classical non-stochastic model with fixed thermodynamic parameters, the literature gives a nucleation range of 300 Kelvins. So we are unable to reject or accept any of this because we don't have a valid experimental proof. So we suggest we are having a different result, but we have to have further experimental validation to see which one is actually reporting the right one. So we again tried with the similar composition of the reported value, and we are getting just 2 Kelvin nucleation range. So our conclusions are that model requires very few input data from the user and works with live thermodynamic data. Model can predict individual nucleation event in agreement to current knowledge base. Range of nucleation is different from the previously reported values. Nucleation temperature prediction is sensitive to droplet size, gas properties, and composition. Stochastic aspect is resembling the real life scenario and presents a band of nucleation temperature, and a change in time step didn't change the nucleation temperature results for the model, and the model predicts smaller droplets nucleates at a lower temperature, and cooling rate is inversely proportional to the particle size. So yeah, thank you.